Picture this, a bustling city on Mars with towering domes housing lush green parks, families strolling under a reddish sky, and children playing in gravity that feels like a gentle bounce. Now imagine floating cities above Venus, where humans live in cloud-like habitats, shielded from the scorching surface below. Or picture a thriving lunar colony, where Earth's closest neighbor has become a hub of innovation and exploration. These aren't scenes from a sci-fi movie, they're visions of what could be possible if we dared to reshape other worlds. But here's the big question: with the technology we have today, could we really transform Mars, Venus, or even the Moon into places where humans could live and thrive? This is the concept of terraforming, altering a planet or moon's environment to make it habitable for humans. It's a dream that has fascinated scientists, writers, and dreamers for decades. But is it just a dream, or could it become reality? In this video, we'll explore the incredible potential and the daunting challenges of terraforming these celestial bodies using the tools and knowledge we have right now. From creating breathable atmospheres to protecting against deadly radiation, the journey to making other worlds livable is as thrilling as it is complex. So buckle up, because we're about to dive into one of the most ambitious ideas humanity has ever conceived. Could we really terraform Mars, Venus, and the Moon with today's technology? Let's find out. Now, turning to the heart of the matter, let's break down what terraforming really means. At its core, terraforming is the process of transforming a planet or moon's environment to make it more Earth-like, essentially creating a world where humans could live without the need for constant life support. It's about reshaping an alien landscape into something familiar, something habitable. But how exactly would we do that? The key lies in addressing four critical factors: atmosphere, temperature, water, and soil. First, atmosphere. Humans need air to breathe, and not just any air, oxygen-rich air. Right now, Mars has a thin atmosphere made mostly of carbon dioxide. Venus is shrouded in a thick, toxic blanket of carbon dioxide and sulfuric acid, and the Moon has virtually no atmosphere at all. To make these worlds livable, we'd need to either create or thicken their atmospheres, ensuring they contain the right mix of gases to support life. Next, temperature. Mars is freezing, with average temperatures around -60 degrees Celsius. Venus, on the other hand, is a scorching inferno, with surface temperatures hot enough to melt lead. The Moon swings between extreme heat and cold, depending on whether it's in sunlight or shadow. Terraforming would require stabilizing these temperatures, bringing them into a range where humans could survive comfortably. Then there's water. It's essential for life as we know it, and while Mars has water ice at its poles and possibly underground, Venus and the Moon are far drier. We'd need to find ways to extract, transport, or even create water on these worlds to sustain human colonies. Finally, soil. Plants need nutrients to grow, and without fertile soil, agriculture would be nearly impossible. Mars has a dusty, iron-rich surface, but it lacks the organic matter needed for farming. Venus's surface is hostile to life, and the Moon's soil, or regolith, is barren. Terraforming would involve enriching these soils to support crops and ecosystems. So why focus on Mars, Venus, and the Moon? Mars is the most Earth-like of the three, with a day length similar to ours and evidence of past water. Venus, despite its harsh conditions, has an atmosphere that could potentially be modified, and its gravity is close to Earth's. The Moon, while lacking an atmosphere, is our closest celestial neighbor, making it an ideal testing ground for terraforming technologies. Each of these worlds presents unique challenges but also unique opportunities. And as we'll see, the journey to making them habitable is as much about innovation as it is about imagination. Now turning to Mars, let's explore why it's often seen as the most promising candidate for terraforming. One of the biggest advantages Mars has is its proximity to Earth. At an average distance of about 225 million kilometers, it's one of our closest planetary neighbors, making it a more practical target for missions compared to more distant worlds. This proximity also means shorter travel times, which is crucial for transporting materials, equipment, and eventually people. Another key factor is the presence of water ice on Mars. We've discovered significant amounts of ice at its poles, and there's evidence of subsurface ice in other regions as well. Water is essential not just for drinking, but also for growing food, generating oxygen, and even producing fuel. If we can tap into these icy reserves, it could provide a critical resource for sustaining human life on the red planet. Mars also has a relatively stable climate compared to other celestial bodies. Its day is just over 24 hours long, similar to Earth's, which would make it easier for humans to adapt. The planet experiences seasons, though they're longer due to its more elliptical orbit, and its axial tilt is comparable to Earth's, which helps regulate temperature patterns. These factors make Mars a more familiar environment compared to the extreme conditions on Venus or the Moon. However, Mars isn't without its challenges. Its atmosphere is incredibly thin, about 1% the density of Earth's, and composed mostly of carbon dioxide. This means there's very little oxygen to breathe, and the low atmospheric pressure would make it difficult for humans to survive without protective suits. Additionally, Mars lacks a global magnetic field, which exposes its surface to harmful solar and cosmic radiation. Over time, this radiation could pose serious health risks to colonists and make long-term habitation more complicated. So, how could we address these challenges with today's technology? One approach is to thicken Mars' atmosphere by releasing carbon dioxide trapped in its polar ice caps and soil. This could be done using heat or chemical processes to sublimate the ice and release the gas. Another idea is to import gases from other sources, such as comets or asteroids, to help build up the atmosphere. While these methods are theoretically possible, they would require massive amounts of energy and time. To protect against radiation, we could create artificial magnetic fields using advanced technology or build habitats underground where the Martian soil would act as a natural shield. These solutions are still in the experimental stages, but they show promise for making Mars a safer place to live. In short, Mars offers a unique combination of opportunities and challenges. Its proximity, water resources, and stable climate make it an attractive target for terraforming, but its thin atmosphere and lack of a magnetic field present significant hurdles. With current technology, we're beginning to see how these obstacles might be overcome, but the journey to making Mars habitable will require innovation, determination, and a lot of hard work. Now turning to the challenge of creating a Martian atmosphere, let's explore how we might thicken it to support human life. One of the most discussed methods involves releasing carbon dioxide trapped in Mars' polar ice caps and soil. By heating these regions, either through orbital mirrors or targeted industrial processes, we could sublimate the ice, releasing CO2 into the atmosphere. This would not only increase atmospheric pressure but also help trap heat, raising the planet's temperature, a crucial step toward making Mars more Earth-like. Another approach is importing gases from external sources, such as comets or asteroids rich in volatile compounds like ammonia or methane. These gases could be transported to Mars and released into the atmosphere, further thickening it. While this idea sounds like science fiction, it's theoretically possible with current technology. However, the scale of such an operation would be enormous, requiring advanced spacecraft and precise calculations to ensure the gases are delivered safely and effectively. But thickening the atmosphere isn't without risks. One major concern is the potential for a runaway greenhouse effect. If too much CO2 is released too quickly, it could trap excessive heat, leading to uncontrollable warming. This could destabilize the planet's climate, making it even harder to create a stable, habitable environment. Balancing the release of gases with careful monitoring and control would be essential to avoid such scenarios. Technologically, we're already making strides in this direction. Instruments like the Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, have demonstrated the ability to produce oxygen from Martian CO2. Scaling up such technologies could play a key role in not only generating breathable air but also contributing to atmospheric thickening. However, the energy requirements for these processes are significant, and we'd need to develop robust power sources, such as nuclear reactors or large-scale solar arrays, to make them viable. In summary, creating a thicker atmosphere on Mars is a complex but achievable goal with today's technology. By leveraging methods like releasing CO2 from polar ice caps or importing gases from space, we could take the first steps toward making the red planet more hospitable. However, we must proceed cautiously to avoid unintended consequences, ensuring that our efforts lead to a stable and sustainable environment for future human settlers. Now turning to the challenge of warming up Mars, let's explore the strategies that could help raise its temperature to a level where liquid water can exist, a critical step for making the planet habitable. One of the most intriguing ideas involves using orbital mirrors, massive reflective structures placed in space to redirect sunlight onto Mars' surface. These mirrors could focus solar energy on specific regions, such as the polar ice caps, to melt the ice and release water vapor and carbon dioxide into the atmosphere. This would not only increase the planet's temperature but also contribute to thickening its atmosphere, creating a positive feedback loop for warming. Another approach is the introduction of greenhouse gases such as methane or ammonia into the Martian atmosphere. These gases are highly effective at trapping heat, and even small amounts could significantly raise the planet's temperature. One proposal suggests using factories or automated systems to produce these gases on Mars, using resources already present on the planet. For example, methane could be synthesized from carbon dioxide and hydrogen, both of which are abundant on Mars. Over time, this could create a warmer, more stable climate capable of supporting liquid water. However, these methods come with significant challenges. Orbital mirrors, while theoretically feasible, would require enormous resources to construct and deploy. The mirrors would need to be kilometers wide to have a meaningful impact, and launching such massive structures into space would demand advancements in materials science and space transportation. Similarly, producing greenhouse gases on Mars would require substantial energy and infrastructure, which we currently lack. The energy demands alone could be a major bottleneck, as Mars receives only about half the sunlight Earth does, making solar power less efficient. Another limitation is the time scale involved. Warming Mars would likely take centuries, if not longer, even with the most optimistic projections. The planet's current average temperature is around -60 degrees Celsius, and raising it to a point where liquid water can exist would require a sustained, long-term effort. This raises questions about the practicality of such projects with today's technology and whether humanity is prepared to commit to such a monumental task. Despite these challenges, the potential rewards are immense. A warmer Mars with liquid water could support agriculture, provide drinking water for settlers, and even enable the growth of ecosystems. The key will be developing technologies that are not only effective but also sustainable, ensuring that our efforts to warm Mars don't create new problems in the process. As we continue to explore these possibilities, the dream of a habitable Mars remains within reach, even if the path forward is fraught with obstacles. Now turning to the critical challenge of producing oxygen on Mars, let's explore how we might generate breathable air on a planet where the atmosphere is 95% carbon dioxide. One of the most promising technologies is MOXIE, short for Mars Oxygen In Situ Resource Utilization Experiment. This device, already tested on the Perseverance rover, works by extracting carbon dioxide from the Martian atmosphere and converting it into oxygen through a process called electrolysis. While MOXIE is currently a small-scale experiment, It demonstrates the potential for producing oxygen on Mars using local resources. Scaling this technology to support a human population, however, presents significant hurdles. A single MOXIE unit produces only about 10 grams of oxygen per hour, enough for a small animal, but far from what humans would need to survive. To support even a small group of settlers, we would need thousands of these devices, along with a reliable energy source to power them. Another approach involves using biological systems, such as algae or bacteria, to produce oxygen. Certain types of cyanobacteria, for example, are capable of photosynthesis, converting carbon dioxide and sunlight into oxygen. These organisms could be cultivated in controlled environments, such as greenhouses or bioreactors, to generate breathable air while also providing a potential food source. However, this method comes with its own set of challenges. Mars' thin atmosphere and intense radiation make it difficult to maintain stable conditions for biological systems. Additionally, scaling these systems to produce enough oxygen for a large population would require vast amounts of space and resources, which are limited on Mars. A third option is to import oxygen from Earth or other sources, but this would be incredibly costly and impractical in the long term. Transporting oxygen to Mars would require frequent resupply missions, each costing billions of dollars and consuming valuable payload capacity. This makes in situ production the most viable option despite the technical challenges. The key to overcoming these challenges lies in innovation and efficiency. Advances in material science could lead to more efficient oxygen production systems, while improvements in energy storage and generation could provide the power needed to run these systems at scale. Additionally, integrating multiple approaches such as combining MOXIE-like devices with biological systems could create a more robust and sustainable oxygen supply. As we look to the future, the ability to produce oxygen on Mars will be a cornerstone of any successful terraforming effort. Without breathable air, human life on the Red Planet is impossible. While the challenges are significant, the progress made so far gives us hope that this critical hurdle can be overcome. With continued research and development, the dream of a self-sustaining Martian colony moves closer to reality. Now turning to the critical issue of protecting Mars from radiation, we must address one of the planet's most significant challenges: the lack of a magnetic field. Unlike Earth, Mars does not have a global magnetic shield to deflect harmful cosmic rays and solar radiation. This poses a serious threat to human health, as prolonged exposure to high levels of radiation can lead to cancer, DNA damage, and other life-threatening conditions. For any long-term human presence on Mars, finding a solution to this problem is absolutely essential. One potential solution is to create an artificial magnetic field. Scientists have proposed the idea of generating a magnetic shield around Mars by placing a powerful magnet at a stable point between the planet and the Sun. This magnet could deflect charged particles, mimicking the protective effect of Earth's magnetic field. While this concept is theoretically possible, the technology required to build and deploy such a system is far beyond our current capabilities. It would require massive amounts of energy and materials, as well as advancements in space engineering that we have yet to achieve. Another approach is to build underground habitats. By constructing living spaces beneath the Martian surface, we could use the planet's soil and rock as a natural barrier against radiation. This method is more feasible with today's technology, as it relies on existing construction techniques and materials. Underground habitats would also provide additional benefits, such as insulation from extreme temperature fluctuations and protection from micrometeorite impacts. However, this solution comes with its own challenges. Excavating and building underground structures on Mars would require advanced robotics and significant resources, not to mention the psychological impact of living in confined, subterranean spaces for extended periods. A third option is to use radiation-absorbing materials in the construction of surface habitats. Materials like polyethylene or water-rich compounds could be incorporated into walls and shielding to reduce radiation exposure. While this method would not eliminate the risk entirely, it could significantly lower radiation levels inside habitats, making them safer for human occupants. Combining this approach with underground structures or artificial magnetic fields could create a multi-layered defense system, further enhancing protection. The feasibility of these solutions depends on advancements in technology and our ability to innovate. While creating an artificial magnetic field remains a distant possibility, building underground habitats and using radiation-absorbing materials are more achievable with current technology. As we continue to explore and develop these ideas, the dream of a safe and habitable Mars becomes more attainable. Protecting humans from radiation is not just a technical challenge, it's a fundamental requirement for the future of Martian colonization. With continued research and collaboration, we can find ways to overcome this obstacle and pave the way for a thriving human presence on the Red Planet. Now turning to Venus, often referred to as Earth's evil twin, we encounter a planet that presents some of the most extreme challenges for terraforming. With surface temperatures soaring to over 450 degrees Celsius, a crushing atmospheric pressure 92 times that of Earth, and clouds of sulfuric acid, Venus is a true hellscape. These conditions make it seem like an unlikely candidate for human habitation. Yet, despite its harsh environment, Venus holds intriguing potential for transformation, offering unique opportunities for those daring enough to reimagine its future. One of the most striking features of Venus is its thick atmosphere, composed almost entirely of carbon dioxide. This dense blanket of gas traps heat in a runaway greenhouse effect, creating the scorching temperatures that make the planet's surface uninhabitable. However, this very atmosphere could also be the key to its transformation. If we could find a way to remove or convert the excess carbon dioxide, we might be able to cool the planet and create conditions more suitable for life. Another challenge is the sulfuric acid clouds that shroud Venus in a toxic haze. These clouds reflect much of the sunlight that reaches the planet, contributing to its extreme heat while also making the surface a hostile environment. Yet, these clouds also float in a region of the atmosphere where temperatures and pressures are surprisingly Earth-like. This has led some scientists to propose the idea of floating habitats in Venus' upper atmosphere, where humans could live and work without needing to tackle the planet's surface directly. Despite its daunting challenges, Venus is often overlooked in discussions of terraforming, overshadowed by the more familiar and seemingly more achievable goal of colonizing Mars. However, Venus offers unique advantages such as its proximity to Earth and its similar size and gravity, which could make long-term human habitation more comfortable compared to smaller bodies like Mars or the Moon. Additionally, the planet's thick atmosphere could provide a natural shield against radiation, reducing the need for artificial protection. The potential for transforming Venus lies in our ability to think creatively and push the boundaries of current technology. While the challenges are immense, the rewards could be equally groundbreaking. By exploring innovative solutions such as atmospheric filtering, solar shades, or even floating cities, we might one day unlock the secrets of this enigmatic planet and turn it into a second home for humanity. Venus may be a hellish world today, but with ingenuity and determination, it could become a beacon of hope for the future of space exploration. Now turning to the challenge of cooling down Venus, we face one of the most daunting tasks in terraforming, reducing its surface temperature, which currently exceeds 450 degrees Celsius. This extreme heat is a direct result of the planet's thick carbon dioxide atmosphere, which traps heat in a runaway greenhouse effect. To make Venus habitable, we would need to find a way to significantly lower its temperature, creating conditions that could support liquid water and, eventually, life. One proposed method for cooling Venus is the use of solar shades. These massive structures placed in orbit around the planet would block a portion of the sunlight reaching Venus, reducing the amount of heat absorbed by its atmosphere. Over time, this could help lower the planet's surface temperature to more manageable levels. However, the scale of such a project is staggering. Building and deploying solar shades large enough to have a meaningful impact would require advancements in materials science, space construction, and energy efficiency that are currently beyond our capabilities. Another approach involves atmospheric filtering, where we would remove or convert the excess carbon dioxide in Venus' atmosphere. This could be achieved through chemical processes that break down carbon dioxide into oxygen and carbon, or by introducing organisms or machines capable of absorbing and storing the gas. While this method addresses the root cause of Venus' extreme heat, it also presents significant technological hurdles. The sheer volume of carbon dioxide in Venus' atmosphere is immense, and developing systems capable of processing it on such a scale would require breakthroughs in both engineering and biotechnology. Current advancements in technology offer some hope, but they are not yet sufficient to make these methods feasible. For example, while we have made progress in developing lightweight materials for space construction, creating structures as large as solar shades remains a distant possibility. Similarly, while we have experimented with carbon capture technologies on Earth, scaling these systems to handle the atmosphere of an entire planet is a monumental challenge. Despite these obstacles, the idea of cooling Venus is not entirely out of reach. With continued innovation and international collaboration, we may one day develop the tools and techniques needed to tackle this ambitious goal. The journey to transform Venus into a habitable world will be long and fraught with challenges, but the potential rewards, a second Earth-like planet within our solar system, are worth the effort. As we push the boundaries of what is possible, Venus stands as a testament to the power of human ingenuity and the enduring dream of exploring and reshaping new worlds. Now turning to the challenge of removing Venus' toxic atmosphere, we encounter one of the most complex aspects of terraforming this hostile planet. Venus' atmosphere is not only thick with carbon dioxide, but also laced with sulfuric acid clouds, making it a corrosive and inhospitable environment. To transform Venus into a habitable world, we would need to address both the overwhelming density of carbon dioxide and the presence of these acidic clouds, which pose significant risks to any potential human presence or infrastructure. One potential solution is chemical conversion, where we would use advanced chemical processes to break down carbon dioxide into oxygen and carbon. This could involve deploying large-scale reactors or chemical plants on Venus' surface or in its atmosphere. These systems would need to be incredibly robust to withstand the planet's extreme conditions, including high temperatures and corrosive clouds. While we have made strides in carbon capture and conversion technologies on Earth, scaling these systems to handle the entire atmosphere of Venus is a monumental task. The sheer volume of carbon dioxide, nearly 96 times the amount found on Earth, means that even the most efficient systems would require decades, if not centuries, to make a noticeable impact. Another approach is atmospheric stripping, where we would remove excess carbon dioxide and sulfuric acid from Venus' atmosphere entirely. This could be achieved through methods like using powerful magnetic fields to deflect charged particles or deploying massive orbital structures to siphon off atmospheric gases. While these ideas are theoretically possible, they would require technologies far beyond our current capabilities. For instance, creating a magnetic field strong enough to influence Venus' atmosphere would demand an unprecedented amount of energy and materials. Similarly, constructing orbital structures capable of filtering or removing gases on such a scale would involve overcoming immense engineering and logistical challenges. Despite these hurdles, there are some promising avenues for progress. For example, researchers have explored the possibility of using genetically engineered microorganisms or synthetic biology to absorb and process carbon dioxide and sulfuric acid. These organisms could be designed to thrive in Venus' harsh conditions, gradually transforming the atmosphere over time. While this approach is still in its early stages, it represents a creative and potentially scalable solution to one of the most daunting problems in terraforming. Current technology, however, is not yet advanced enough to make these methods feasible. The challenges of working in Venus' extreme environment, combined with the scale of the task, mean that any serious effort to remove its toxic atmosphere would require breakthroughs in multiple fields, from materials science to biotechnology. Yet, the dream of transforming Venus into a habitable world continues to inspire scientists and engineers, driving innovation and pushing the boundaries of what we believe is possible. As we look to the future, the removal of Venus' toxic atmosphere remains a key step in the long journey toward terraforming. While the road ahead is filled with challenges, the potential rewards, a second Earth-like planet within our solar system, are worth the effort. With continued research, collaboration, and ingenuity, we may one day unlock the secrets to transforming Venus into a world where humanity can thrive. Now turning to the idea of creating a habitable surface on Venus, we shift our focus from the planet's toxic atmosphere to its upper layers, where conditions are surprisingly more Earth-like. While the surface of Venus is a scorching inferno with temperatures exceeding 450 degrees Celsius, the upper atmosphere, about 50 kilometers above the surface, offers a more temperate environment. Here, the pressure and temperature are comparable to those on Earth, making it a potential location for floating cities. The concept of floating cities on Venus involves constructing massive, buoyant structures that hover in the planet's upper atmosphere. These habitats would rely on the dense carbon dioxide atmosphere to provide lift, much like a hot air balloon. The idea is both imaginative and practical, as it sidesteps the need to alter the planet's surface or atmosphere on a massive scale. Instead, it leverages the unique properties of Venus' atmosphere to create a livable environment for humans. Building such floating cities would require advanced materials and engineering. The structures would need to be lightweight yet durable enough to withstand the corrosive effects of sulfuric acid clouds and the dynamic atmospheric conditions. One proposed material is aerogel, a lightweight, highly insulating substance that could protect the habitats from extreme temperatures and chemical reactions. Additionally, the cities would need to be self-sustaining, equipped with systems for generating oxygen, recycling water, and producing food, much like a space station but on a much larger scale. Energy would also be a critical factor. Solar power is a viable option in Venus' upper atmosphere, where sunlight is abundant and not blocked by thick clouds as it is on the surface. Solar panels could be deployed to harness this energy, powering the cities and supporting life support systems. However, the technology to build and maintain such large-scale floating habitats is still in its infancy. While we have experience with smaller-scale projects like the International Space Station, scaling up to entire cities presents unprecedented challenges. Another consideration is mobility. Floating cities would need to navigate Venus' upper atmosphere, which is characterized by strong winds and turbulence. This would require advanced propulsion systems and precise control mechanisms to ensure stability and safety. While these technologies exist in some form today, adapting them for use on Venus would require significant innovation and testing. Despite these challenges, the concept of floating cities on Venus is not entirely out of reach. In fact, NASA has already proposed missions like the High-Altitude Venus Operational Concept, or HAVOC, which envisions crewed missions to Venus' upper atmosphere. These missions could serve as a stepping stone, testing the feasibility of long-term habitation and paving the way for larger-scale projects. While the idea of floating cities on Venus may sound like science fiction, it represents a creative and potentially achievable solution to the challenges of terraforming. By focusing on the upper atmosphere, we bypass many of the obstacles posed by the planet's surface and toxic environment. With continued advancements in materials science, energy systems, and aerospace engineering, the dream of building habitable cities in the skies of Venus could one day become a reality. As we explore this possibility, we are reminded that the future of space exploration is limited only by our imagination and determination. Now turning to the Moon, Earth's closest neighbor, we explore another fascinating candidate for terraforming. Unlike Mars or Venus, the Moon offers a unique advantage: its proximity to Earth. Just a 3-day journey away, the Moon could serve as an ideal testing ground for extraterrestrial habitation and the technologies needed to transform hostile environments into livable spaces. However, the Moon presents its own set of challenges, primarily due to its lack of atmosphere and extreme temperature variations. The Moon's surface is a barren, airless landscape with no atmosphere to protect it from the harsh conditions of space. This absence of an atmosphere means there is no natural shield against solar radiation, micrometeorite impacts, or the extreme temperature swings that occur between lunar day and night. During the day, temperatures can soar to around 127 degrees Celsius, while at night they plummet to a frigid -173 degrees Celsius. These conditions make the Moon an unforgiving environment for human life as we know it. Despite these challenges, the Moon's proximity to Earth makes it an attractive candidate for early experiments in terraforming. Its closeness allows for relatively quick communication and transportation, reducing the logistical hurdles compared to more distant destinations like Mars or Venus. Additionally, the Moon's lower gravity, about 1/6 of Earth's, could provide valuable insights into how humans and ecosystems might adapt to extraterrestrial environments. This makes the Moon not just a potential habitat but also a critical stepping stone for future missions to other planets. One of the first steps in making the Moon habitable would be addressing its lack of atmosphere. Without an atmosphere, there is no air to breathe, no protection from radiation, and no way to regulate temperature. Creating even a thin atmosphere on the Moon would require significant technological innovation, such as releasing trapped gases from beneath the lunar surface or importing gases from Earth. While these ideas are still in the realm of theory, they highlight the kind of creative thinking needed to tackle the Moon's challenges. Another major hurdle is stabilizing the Moon's extreme temperature variations. Without an atmosphere to distribute heat, the lunar surface experiences dramatic shifts between scorching days and freezing nights. One proposed solution is the use of reflective surfaces or insulating materials to moderate these temperature swings. Alternatively, habitats could be built underground or within lava tubes, where the natural insulation of the Moon's crust could provide a more stable environment. Water, a critical resource for any terraforming effort, has also been discovered on the Moon, primarily in the form of ice trapped in permanently shadowed craters near the poles. Extracting and utilizing this water would be a game changer, providing not only a source of drinking water, but also the raw materials for producing oxygen and hydrogen, which could be used for fuel and life support systems. However, the technology to efficiently mine and process lunar water is still in its early stages, requiring further development and testing. As we consider the Moon's potential for terraforming, it's clear that while the challenges are significant, the opportunities are equally compelling. The Moon's proximity to Earth, combined with its unique environment, makes it an invaluable testing ground for the technologies and strategies we'll need to transform other worlds. By tackling the Moon's challenges, we can gain the knowledge and experience necessary to take the next giant leap in space exploration. Now turning to the challenge of building a lunar atmosphere, we delve into one of the most critical steps in making the Moon habitable. Without an atmosphere, the Moon remains a harsh, airless environment, incapable of supporting human life as we know it. But could we create even a thin atmosphere on the Moon using today's technology? Let's explore the possibilities. One proposed method involves releasing trapped gases from beneath the Moon's surface. Scientists believe that certain gases such as carbon dioxide, nitrogen, and even water vapor may be locked within the lunar regolith or deep underground. By heating the regolith or drilling into the moon's crust, we could potentially release these gases, gradually building up a thin atmosphere. While this idea is theoretically sound, the technology to efficiently extract and release these gases on a large scale is still in its infancy. It would require advanced mining equipment and energy sources capable of operating in the moon's low-gravity, high-radiation environment. Another approach is importing gases from Earth. This would involve transporting large quantities of nitrogen, oxygen, and other essential gases to the moon, either by spacecraft or through some form of mass driver system. While this method could provide a more controlled and predictable way to create an atmosphere, the logistical challenges are immense. Transporting enough gas to make a meaningful difference would require an enormous amount of energy and resources, making it a costly and complex endeavor with current technology. Even if we could create a thin atmosphere, maintaining it would be another hurdle. The moon's low gravity means that gases would escape into space more easily than on Earth. To counteract this, we would need to continuously replenish the atmosphere or find ways to trap gases near the surface. One idea is to use magnetic fields or electrostatic forces to hold gases in place, but these solutions are still in the experimental stage and far from practical application. Despite these challenges, the idea of building a lunar atmosphere is not entirely out of reach. Advances in robotics, energy production, and materials science could make these methods more feasible in the coming decades. For now, however, creating a stable atmosphere on the moon remains a significant technological hurdle, requiring innovative solutions and international collaboration. As we consider the practicality of these ideas, it's clear that while the moon's proximity to Earth offers unique opportunities, the challenges of building an atmosphere are formidable. Yet, by tackling these challenges, we can pave the way for future lunar habitats and gain invaluable experience for terraforming other worlds. Moving forward, the next step in our lunar terraforming journey involves stabilizing the moon's extreme temperature variations, a critical factor in creating a livable environment. Now turning to the challenge of stabilizing the moon's temperature, we face one of the most critical obstacles in making it habitable. The moon experiences extreme temperature swings, ranging from scorching highs of around 127 degrees Celsius during the day to freezing lows of -173 degrees Celsius at night. These drastic fluctuations make it nearly impossible for humans to survive without advanced technology. So, how could we moderate these temperature swings using today's tools and ideas? One promising approach involves using reflective surfaces to manage heat. By covering large areas of the moon's surface with highly reflective materials, we could reduce the amount of solar radiation absorbed during the day, preventing the surface from overheating. At night, these same surfaces could help retain heat, creating a more stable thermal environment. While this concept is straightforward in theory, implementing it on a lunar scale would require massive amounts of material and energy. Additionally, maintaining these surfaces in the moon's harsh environment, with its constant bombardment of micrometeorites and radiation, would pose significant engineering challenges. Another solution is to build underground habitats. Beneath the moon's surface, temperatures are far more stable, shielded from the extreme highs and lows of the lunar day-night cycle. By constructing habitats in lava tubes or excavating tunnels, we could create environments that naturally maintain a consistent temperature. This approach would also provide protection from radiation and micrometeorites, making it a dual-purpose solution. However, the technology needed to excavate and reinforce these underground structures on the moon is still in development. Current robotic systems and construction techniques would need significant advancements to make this a viable option. A third idea combines both approaches, using reflective surfaces above ground while creating insulated underground spaces. This hybrid method could offer the best of both worlds, moderating surface temperatures while providing stable, habitable environments below. Yet, even this solution would require overcoming substantial challenges, such as transporting construction materials to the moon and developing energy-efficient systems to maintain these habitats. The challenges of stabilizing the moon's temperature highlight the complexity of creating a livable environment on such an inhospitable world. While the moon's proximity to Earth makes it an attractive candidate for human habitation, its extreme conditions demand innovative solutions and significant technological advancements. As we continue to explore these possibilities, we gain valuable insights that could inform future efforts to terraform not just the moon, but other worlds as well. Moving forward, the next step in our lunar terraforming journey involves harnessing one of the moon's most valuable resources, water. Now turning to the discovery of water on the moon, we uncover a resource that could be a game changer for lunar terraforming. In recent years, scientists have confirmed the presence of water ice in the permanently shadowed craters near the moon's poles. These deposits, hidden from the sun's intense heat, could hold enough water to support human life and even fuel future missions. But why is this discovery so crucial? Water is not just essential for drinking and agriculture. It can also be split into hydrogen and oxygen, providing breathable air and rocket fuel. This makes lunar water a cornerstone for any long-term human presence on the moon. Extracting this water, however, is no simple task. The ice is buried in some of the coldest and darkest regions of the moon, where temperatures can plummet to -250 degrees Celsius. To access it, we would need advanced drilling and mining technologies capable of operating in these extreme conditions. One proposed method involves using robotic rovers equipped with drills and heating systems to melt the ice and collect the water. Another idea is to use solar-powered machines to vaporize the ice and capture the resulting water vapor. Both approaches would require precise engineering to ensure efficiency and reliability in the moon's harsh environment. Once extracted, the next challenge is storing and utilizing this water effectively. On Earth, we take for granted the infrastructure that delivers clean water to our homes and industries. On the moon, we would need to build entirely new systems to transport, purify, and distribute water. This could involve creating pipelines or using tankers to move water from extraction sites to habitats and processing facilities. Additionally, we would need to develop technologies to recycle water efficiently, minimizing waste and ensuring a sustainable supply for future generations. The presence of water on the moon also opens up exciting possibilities for agriculture. With water, we could experiment with growing plants in lunar soil, either in greenhouses or through hydroponic systems. This would not only provide fresh food for astronauts, but also help create a self-sustaining ecosystem. However, growing plants on the moon comes with its own set of challenges, such as low gravity, radiation exposure, and the lack of a natural atmosphere. Overcoming these hurdles would require innovative solutions, from genetically modified crops to advanced shielding techniques. While the discovery of lunar water is a significant step forward, the technology needed to harness it is still in its early stages. Current robotic missions like NASA Artemis program are laying the groundwork by mapping water deposits and testing extraction methods. However, scaling these efforts to support a permanent human presence will require substantial investment and international collaboration. As we continue to explore the moon's potential, the lessons we learn here could pave the way for terraforming other worlds, bringing us closer to the dream of becoming a multi-planetary species. Moving forward, the next phase of our journey involves exploring how we might grow food on the moon, a critical step in making it a truly habitable world. Now turning to the potential for growing food on the moon, we enter a critical phase in making lunar habitation a reality. Agriculture on the moon presents a unique set of challenges, starting with the lack of natural soil. Lunar regolith, the layer of loose material covering the moon's surface, is vastly different from Earth's fertile soil. It lacks organic matter and essential nutrients needed for plant growth. To overcome this, scientists are exploring hydroponic systems where plants grow in nutrient-rich water instead of soil. This method not only bypasses the need for traditional soil, but also allows for precise control over the nutrients plants receive, maximizing growth efficiency. Another major hurdle is the moon's low gravity, which is about 1/6 of Earth's. This reduced gravity can affect how plants absorb water and nutrients, potentially stunting their growth. Researchers are studying how plants adapt to these conditions, with experiments conducted on the International Space Station providing valuable insights. Early results suggest that while some plants can grow in low gravity, their development may be slower or less robust compared to Earth. To address this, scientists are considering genetically modified plants engineered to thrive in lunar conditions, potentially accelerating growth and improving resilience. Radiation is another significant challenge. Without a protective atmosphere or magnetic field, the moon is bombarded by cosmic rays and solar radiation, which can harm both plants and humans. Shielding crops from this radiation is essential, and one proposed solution is to grow plants in underground habitats or within heavily shielded greenhouses. These structures could use materials like lunar regolith or advanced composites to block harmful radiation while allowing sunlight or artificial light to reach the plants. Water, as we've discussed, is a critical resource for lunar agriculture. While the discovery of water ice on the moon is promising, efficiently using this water for farming will require innovative recycling systems. Closed-loop hydroponic systems, which recycle water and nutrients, could minimize waste and ensure a sustainable supply for crops. Additionally, advancements in water extraction and purification technologies will be vital to support large-scale agriculture. Despite these challenges, the potential benefits of lunar agriculture are immense. Growing food on the moon could reduce the need for costly resupply missions from Earth, making long-term habitation more feasible. It could also contribute to creating a self-sustaining ecosystem where plants produce oxygen and help recycle carbon dioxide, further supporting human life. While the technology to achieve this is still in development, ongoing research and international collaboration are bringing us closer to turning this vision into reality. As we look ahead, the lessons learned from lunar agriculture could have far-reaching implications, not just for the moon but for future missions to Mars and beyond. The ability to grow food in space is a cornerstone of sustainable space exploration, and each step forward brings us closer to the dream of becoming a multi-planetary species. With the next phase of our journey in sight, we now turn to the energy sources that will power these ambitious terraforming efforts. We must consider the immense energy requirements needed to transform Mars, Venus, and the Moon into habitable worlds. Terraforming is an energy-intensive process requiring vast amounts of power to alter atmospheres, regulate temperatures, and sustain human life. The question is, can our current energy technologies meet these demands? Solar power is one of the most promising options, especially for the Moon and Mars. Both celestial bodies receive ample sunlight, making solar panels a viable solution. On the Moon, solar arrays could be set up in permanently sunlit regions near the poles, providing a consistent energy supply. Mars, though farther from the Sun, still receives enough sunlight to make solar power feasible, especially with advancements in solar panel efficiency. However, solar energy has its limitations. Dust storms on Mars can block sunlight for extended periods, and the Moon's long nights would require energy storage systems to ensure a continuous power supply. Nuclear energy is another strong contender. Small modular nuclear reactors could provide a reliable and powerful energy source for terraforming projects. These reactors are compact, efficient, and capable of operating in harsh environments, making them ideal for extraterrestrial use. On Mars, nuclear energy could power atmospheric processors and heating systems, while on the Moon, it could support large-scale agriculture and habitat construction. However, the challenges of transporting nuclear materials safely and managing radioactive waste in space remain significant hurdles. Fusion energy, often hailed as the holy grail of power generation, could revolutionize terraforming efforts. Fusion reactors, which mimic the processes powering the sun, offer nearly limitless energy with minimal environmental impact. While fusion technology is still in its experimental stages, breakthroughs in this field could provide the energy needed to sustain large-scale terraforming projects. The challenge lies in developing compact and efficient fusion reactors that can operate reliably in space. Despite these promising options, current energy technologies have limitations. Solar and nuclear power, while effective, may not be sufficient on their own to meet the colossal energy demands of terraforming. Fusion, though potentially game-changing, is not yet a practical solution. This raises the question, will we need to combine multiple energy sources, or will new breakthroughs in energy technology be required to make terraforming a reality? As we explore these possibilities, it's clear that energy is the lifeblood of any terraforming effort. Without a reliable and sustainable energy supply, transforming Mars, Venus, or the Moon into habitable worlds remains a distant dream. Yet, with continued innovation and international collaboration, we may one day unlock the energy solutions needed to turn this vision into reality. With the next phase of our journey in sight, we now turn to the economic and ethical considerations that will shape the future of terraforming. Now turning to the economic and ethical considerations of terraforming, we must confront the monumental costs and moral dilemmas that come with reshaping entire worlds. Terraforming Mars, Venus, or the Moon is not just a scientific challenge, it's a financial and ethical one as well. The sheer scale of these projects would require trillions of dollars, decades of effort, and unprecedented global cooperation. The question is, can humanity justify such an enormous investment, especially when there are pressing needs here on Earth? From an economic perspective, the costs of terraforming are staggering. Building the infrastructure to transport materials, develop energy systems, and sustain human life on another planet or moon would require a level of funding that surpasses even the most ambitious space missions to date. Governments, private companies, and international organizations would need to collaborate on an unprecedented scale, pooling resources and expertise to make such projects feasible. While the potential benefits such as new frontiers for exploration, resource extraction, and even colonization are immense, the financial burden raises serious questions about priorities. Should we invest in solving Earth's problems first, or is the promise of a multi-planetary future worth the cost? Ethically, terraforming presents a host of complex issues. One of the most pressing concerns is the potential impact on any existing microbial life. While we have yet to discover definitive evidence of life on Mars, Venus, or the Moon, the possibility cannot be ruled out. Altering these environments could inadvertently destroy extraterrestrial ecosystems, raising questions about our responsibility as explorers and stewards of the cosmos. Do we have the right to reshape other worlds, even if it means erasing the only life forms that may exist beyond Earth? Beyond the question of life, there's also the ethical dilemma of altering celestial bodies that have existed in their current state for billions of years. Terraforming would fundamentally change the nature of these worlds, raising concerns about preserving their natural state for scientific study and future generations. Some argue that we should focus on adapting to these environments rather than transforming them, using technology to create sustainable habitats without altering the planets or moons themselves. As we weigh these economic and ethical considerations, it's clear that terraforming is not just a technical challenge, it's a profound moral and financial decision. The choices we make today will shape the future of humanity's relationship with the cosmos. With the next phase of our journey in sight, we now turn to the importance of international collaboration in making these ambitious projects a reality. Now turning to the critical role of international collaboration, it's clear that terraforming Mars, Venus, or the Moon is not a task any single nation or organization can tackle alone. The sheer scale and complexity of these projects demand a level of global cooperation unlike anything we've seen before. From sharing resources and expertise to coordinating logistics and funding, the success of terraforming hinges on humanity's ability to work together across borders, cultures, and ideologies. Historically, international space projects have shown both the potential and the challenges of such collaboration. Take, for example, the International Space Station, a marvel of engineering and diplomacy that brought together space agencies from the United States, Russia, Europe, Japan, and Canada. For over 2 decades, the ISS has served as a symbol of what humanity can achieve when we unite for a common goal. However, it also highlights the difficulties of maintaining long-term partnerships, especially in the face of political tensions and shifting priorities. Terraforming would require an even greater level of commitment, with nations and organizations agreeing to invest trillions of dollars and decades of effort into a shared vision. Organizations like NASA and the European Space Agency have already laid the groundwork for such collaboration, with missions like the Mars rovers and the Artemis program demonstrating the benefits of pooling resources and expertise. Private companies like SpaceX are also playing an increasingly important role, bringing innovation and efficiency to the table. Elon Musk's vision of colonizing Mars has sparked global interest, but even SpaceX cannot achieve this alone. The challenges of terraforming, whether it's creating a breathable atmosphere on Mars or cooling down Venus, require a diverse range of skills, technologies, and perspectives that only a truly global effort can provide. Yet, coordinating such a massive undertaking is no small feat. Differences in funding, priorities, and even scientific approaches could create friction among participating nations and organizations. Establishing a framework for decision-making, resource allocation, and conflict resolution will be essential to keeping the project on track. Additionally, the long-term nature of terraforming means that commitments must endure across generations, requiring not just political will but also public support and cultural buy-in. As we look to the future, the dream of terraforming offers a unique opportunity to redefine what it means to work together as a global community. By uniting our efforts, we can turn the vision of habitable worlds beyond Earth into a reality. With the next phase of our journey in sight, we now explore the realistic timeline for terraforming and the stages involved in this monumental endeavor. Now turning to the timeline for terraforming, it's important to approach this monumental task with both optimism and realism. Transforming Mars, Venus, or the Moon into habitable worlds is not something that will happen overnight. In fact, it could take centuries of sustained effort, innovation, and collaboration. Let's break it down into stages to better understand what this journey might look like. The first stage, which we're already in, involves exploration and research. Missions like NASA's Perseverance rover and the Artemis program are laying the groundwork by studying the environments of these celestial bodies. This phase is crucial for gathering data on their atmospheres, geology, and potential resources. For Mars, this could take another 2 to 3 decades as we continue to map its surface, analyze its soil, and search for signs of water. Venus and the Moon, while closer, also require extensive study to determine the feasibility of terraforming. Once we've gathered enough data, the next stage would focus on small-scale experiments. For Mars, this might involve testing technologies like MOXIE, which converts carbon dioxide into oxygen, or deploying solar-powered machines to melt ice and release water vapor into the atmosphere. On the Moon, we could begin constructing habitats and testing methods for creating a thin atmosphere. these experiments would likely span several decades as we refine our techniques and learn from trial and error. The third stage would involve large-scale implementation. For Mars, this could mean deploying massive orbital mirrors to warm the planet or releasing greenhouse gases to thicken its atmosphere. On Venus, we might begin constructing solar shades to cool its surface or developing chemical processes to break down its toxic atmosphere. The Moon could see the construction of underground cities and the extraction of water from its polar ice. This stage alone could take a century or more as we work to create stable, habitable environments. Finally, the last stage would be full-scale transformation and colonization. By this point, Mars might have a breathable atmosphere and liquid water on its surface, while Venus could have floating cities in its upper atmosphere. The Moon could serve as a bustling hub for space exploration, with thriving communities and agriculture. However, even with the best technology, this stage could take several centuries to complete. Throughout this timeline, setbacks and breakthroughs are inevitable. Political, economic, and technological challenges could slow progress, while unexpected discoveries or innovations could accelerate it. The key is to remain committed to the vision and adaptable to change. As we move forward, the dream of terraforming reminds us that the future is not something we wait for, it's something we build one step at a time. Now turning to the future, the dream of terraforming Mars, Venus, and the Moon isn't just about transforming distant worlds, it's about inspiring the next generation of scientists, engineers, and explorers. This vision of creating habitable environments beyond Earth has the power to ignite curiosity and ambition in young minds, encouraging them to push the boundaries of what's possible. Imagine a child today gazing at the stars and dreaming of one day walking on a terraformed Mars or living in a floating city above Venus. That dream could be the spark that drives them to pursue a career in space exploration, engineering, or environmental science. Education plays a crucial role in turning these dreams into reality. By fostering a love for science, technology, engineering, and mathematics, often called STEM, we can equip the next generation with the tools they need to tackle the challenges of terraforming. Schools, universities, and even online platforms can provide the knowledge and skills necessary to innovate and problem solve on a cosmic scale. Programs that encourage hands-on learning, like robotics competitions or space simulation projects, can help students develop the creativity and resilience needed for such ambitious endeavors. Innovation, too, is key. The technologies required to terraform other worlds don't yet exist in their final forms, and it will be up to future generations to invent and refine them. From advanced atmospheric processors to sustainable energy systems, the solutions to these challenges will come from the minds of those who are inspired today. By supporting research and development, and by creating opportunities for collaboration across disciplines, we can ensure that the dream of terraforming continues to evolve and grow. But inspiration isn't just for scientists and engineers, it's for everyone. The idea of transforming other worlds reminds us of our shared potential to shape the future. It challenges us to think bigger, to imagine a world where humanity thrives not just on Earth, but across the solar system. And it invites us all to contribute, whether by pursuing a career in space exploration, supporting scientific research, or simply sharing the wonder of these possibilities with others. As we look to the stars, let's remember that the journey of terraforming is as much about the people who will make it happen as it is about the technology. By inspiring the next generation, we're not just building a future for humanity, we're building a future with humanity, one where curiosity, creativity, and collaboration lead the way. So, what role will you play in this incredible story? The possibilities are as vast as the universe itself. Now turning to the conclusion, let's reflect on the incredible journey we've taken through the possibilities and challenges of terraforming Mars, Venus, and the Moon with today's technology. We've explored how Mars, with its water ice and relatively stable climate, stands as the most promising candidate despite the hurdles of its thin atmosphere and lack of a magnetic field. Venus, though a hellish planet with extreme temperatures and a toxic atmosphere, offers intriguing possibilities like floating cities in its upper atmosphere. And the Moon, our closest neighbor, presents a unique testing ground for extraterrestrial habitation, with its water ice deposits and proximity to Earth. Each of these celestial bodies holds immense potential, but the road to transforming them into habitable worlds is fraught with challenges. From creating atmospheres and stabilizing temperatures to generating oxygen and protecting against radiation, the technological hurdles are significant. Yet, as we've seen, current advancements in science and engineering offer glimpses of hope. Whether it's through orbital mirrors, atmospheric processors, or innovative energy solutions, humanity is steadily inching closer to making these dreams a reality. But terraforming isn't just about the technology, it's about the vision, the collaboration, and the inspiration it sparks. It's about pushing the boundaries of what we believe is possible and daring to imagine a future where humanity thrives beyond Earth. It's a reminder that the challenges we face today are opportunities for the next generation to innovate, create, and lead us into a new era of exploration. So, as we conclude this exploration, let's leave you with this thought. The future of space exploration is not just in the hands of scientists and engineers, it's in yours too. Whether you're a student, a dreamer, or simply someone who looks up at the night sky with wonder, you have a role to play in this incredible story. Stay curious, stay engaged, and keep imagining the possibilities. The universe is vast and the journey is just beginning. What will you contribute to the future of humanity among the stars? Don't forget to like, subscribe, and hit the notification bell to stay updated on our next adventures into the cosmos. Together, let's keep exploring the wonders of the universe.